Okay, so my course will be on geometric discrepancy theory, and the lectures will cover several different aspects of geometric discrepancy theory, in particular the use of analysis in this theory. Today I will speak about the so-called orthogonal function method, or you can call it wavelet method in discrepancy theory, which goes back to Klaus Roth. So I will go right into the definitions, and these definitions will sort of explain what's going on and what discrepancy theory is about. So, okay. So basically in discrepancy theory, one of the things you try to understand is how well you can approximate uniform distributions or Lebesgue measure or some other measure by discrete finite sets of points. And there are, of course, many different ways to measure how well distributed points are, and different types of discrepancy provide different way to evaluate the equidistribution. Okay, by the way, please feel free to stop me if you have any questions or you don't understand something that I said. Okay, so I will start with one of the most popular problems in discrepancy here, was one of the most popular settings. So this will be the setting of axis parallel rectangle. So what we deal with here is the following. So we start, we'll work in the unit cube, 0, 1 to the d-dimensional unit cube. You can, for many problems, you can think about d equal to 2. Okay, so assume you have a set of n points in the cube. You want to measure how well distributed they are. One of the ways to do it is use some test sets, then take that test set. In this case, this will be an axis parallel rectangle here. Okay, and you count how many points. This will always stand for cardinality, or the number of elements. How many points are in that rectangle? Okay, then minus n times the volume of this rectangle. So if the distribution is truly uniform, so the expectation of the points were random, for example, the expectation would be exactly n times the volume of the area. Okay, actually, it might be a little bit clearer if you normalize by n. Actually, in some books, you would see it normalized by n, in some books not normalized by n. So if you normalize by n, you would be measuring the proportion of the points minus the area. Okay, so that's the error. It tells you the imperfections of the distribution. Okay, and then we take the supremum over some class of sets, and in particular, in this case, our class of sets will be axis parallel rectangles, all possible axis parallel rectangles. Okay, so you're finding the worst possible error. Okay, and then you're taking the infimum over all sets of n points. That means you are looking for the best distributed set of n points. So the setting is clear, I hope. In this particular case, when we talk about axis parallel rectangles, some of the natural guesses might be wrong. So in particular, you might say, well, we want to put points on a natural grid. It's not a very good picture on a square grid. But a square grid is not very good, because with a square grid, if you have too many points along one line, you can choose a very, very thin rectangle which contains many points, so this number will be large, but the area is almost 0, so this number almost disappears, which makes the discrepancy large. So that's not a very good distribution from this point of view. Okay, right now you are wondering, where is analysis in all of this, and also why we care about such things. Well, well-distributed points arise in many different problems. In particular, one of the problems is finding good cubature formulas, finding ways to approximately evaluate integrals, and this is one of the ways to measure the quality. I will not go into these details, but I will answer the other question: where is analysis in this? Well, okay, so here we deal with axis parallel rectangles. I'll slightly simplify the problem. I'll consider just the rectangles that are anchored at the origin, rectangles that look like this. Okay, and if you think about it for a second, if you don't care much about the constants, it doesn't matter much, because you can take any such rectangle and you can write it as a combination, the unions and differences of these rectangles anchored at the origin. So this is what we'll deal with. So we'll call this the discrepancy function. One of the nice things about it is now the discrepancy is a function of this upper right corner, okay, or the opposite corner, opposite to the origin if you're in higher dimensions. Okay. All right, so then you define the discrepancy this way. The volume is simply the product of the coordinates here, okay, and you have a function. So you can try analyzing this function, try to analyze its behavior. When we talk about the supremum of the discrepancy, this is, you're looking at the L infinity norm, right? And this function is piecewise continuous, so this L infinity norm is really the supremum. You can also look at other norms, LP norms of this function, and they give you different information about equidistribution, about how well distributed the points are. Also, sometimes dealing with LP norms is easier, in particular with L2 norms. This is something that we will see very soon in just a few minutes. We know that there are lots of methods for dealing with the L2 norm. It's easier to compute the L2 norm than to find the maximum disruption. And also, if you know something about the LP norms, say the L2 norm, if you know something about the L2 norm, then you can say, well, the L infinity norm is bigger, the supremum is bigger than the average, right? So that gives you some partial information. So I will go straight to one of the main theorems that I want to talk about today, and this is the theorem of Roth, who died about 11 years ago. So this theorem says the following. Let me read it. So it gives a lower bound for the L2 discrepancy, and as I just said, then this in particular gives a lower bound for the L infinity for the extremal discrepancy, just because it's bigger. Okay, and the lower bound is the following. So there is some dimensional constant, so that asymptotically the L2 discrepancy grows at least as log n to the d minus 1 over 2. Okay, so that means that no matter how you choose endpoints, you can never make discrepancies smaller than that. And that's actually the reason for the name of this paper on regularities of distribution. So basically this is saying that any distribution is irregular. Discrepancy has to grow with n at least this rate. Okay, we will see in just a few minutes where the logarithm comes from, where the power d minus 1 comes from. So actually they will turn out to be quite natural. Klaus Roth was a very famous mathematician. He got a Fields Medal in 1958, if I'm not mistaken. He got it for very different work. He got it for his work in Diophantine approximation, but according to his own words, this was his favorite result. Okay, of his. I know it independently from William Chen and Kenneth Stolarsky. Actually, on Wednesday, Stolarsky's name will come up. And also, there is a written confirmation from Ben Green. So when Klaus Roth died, Terry Tao had a blog post about Klaus Roth, and here Ben Green mentions this, that I asked him what his favorite proof among his results was, and he said the lower bound for the L2 discrepancy of point sets with respect to axis parallel boxes. It's a very elegant argument that we will see today. Okay, and as far as I know, according to his own words, he liked this result so much, both because it was elegant, but also because it essentially started the theory. And the fact that it started the theory actually could be seen from a lot of papers and even a book which have almost the same name as the name of his original paper on regularities of distribution. So this became a very popular name. There are quite a few papers by famous mathematicians. Okay. I want to mention, so this slide I assume will be online, and I want to mention a few books on the subject. It's a pretty rich subject with very different directions, very different problems, very different methods. So there are many different books. I particularly like the book that I marked here in yellow. This is the book by Matoshek, who unfortunately also died the same year. He died pretty young, but he wrote books beautifully. So if you want to read something which would give you a gentle introduction, I really recommend that book. Some of the things that I will describe in my lectures are contained in this book. Some are not, which actually shows that the theory is actually quite large. This book is super reader friendly. You can open it on pretty much any page and start reading, and it reads really, really well. When I was studying this theory, I used it as bedtime reading. Okay. Um, okay, so specific reference relevant to this lecture, a couple surveys that I wrote, and also a survey lecture notes by my colleague and collaborator, Michael Lacey. You can feel free to look at them. But now let's actually go back to the theorem. So actually here's a slightly more general theorem. So theorem of Claus-Roth corresponds to p equal to 2, but actually it holds for all p between 1 and infinity, strictly between 1 and infinity. And well, the case p greater than 2 is almost obvious because the LP norms are greater than L2 norms if p is greater than 2. So the case between 1 and 2 is interesting. And you can notice that there were 20 years, more than 20 years between the two results. Actually, what's interesting is that using modern harmonic analysis, this result can be extended in about 5 lines. But well, to be completely honest, in that period, those methods of harmonic analysis were just being developed. Okay. So turns out that the theorem of Roth and its extension by Schmidt are actually sharp. So there are numerous constructions of point sets, and we'll talk about them a little bit, which actually achieve this rate of discrepancy. And by the way, when I use this symbol here, I always mean that there exists some constant. The constant usually depends on the dimension, but not on the point distribution, not on n. So I will be interested in asymptotics in n. So low bounds for us will mean that no matter how you choose the point set, you have a lower bound. You cannot make the discrepancy smaller. Upper bounds will mean that we can find the set that achieves that rate of discrepancy. Okay, so for LP norms between 1 and infinity, sharp bounds are known. And what we're going to do next is we will actually prove this bound for p equal to 2. We will prove Roth's original theorem. And we will more or less use the same method that he used with some minor adaptations. Okay. All right, so I'll introduce his big contribution here. The big idea was to use orthogonal functions to analyze the discrepancy function, and in particular used Haar functions. Now, Haar functions were invented in 1909 by Haar, and they are known as the first examples of waves. So some of you might know what wavelets are, some not. The word wavelet did not exist back then. I think it appeared probably in the 1970s. But basically, wavelets are orthogonal bases that are localized both in time and frequency. Well, one of the most common orthogonal bases that you know is the Fourier bases, sines and cosines. They're localized in frequency. They have one single frequency. They have one single oscillation. Right? Sorry, the picture, they're not very good, but they're not localized in time. This wave goes forever. For many applications, it's much more convenient to have bases that are localized both in time and frequency. So here's how Haar functions work. So you start with the system of so-called dyadic intervals. Dyadic is essentially another word for binary. So these are intervals of length 2 to the negative n. And basically what you do is at level 0, you take the whole interval 0, 1. At level 1, you take these two subintervals. Okay. Then you further subdivide them into 4 intervals. Those are dyadic intervals of level 2, and so on. Okay, you keep subdividing the intervals. And then one of the properties that if you take a dyadic interval, and because of the construction, the left and right sides are also dyadic. Okay, so the Haar function is defined as follows. It's -1 on the left half and +1 on the right half. So for every dyadic interval, you can divide the Haar function, and otherwise it's 0. So you see that it's an oscillation that's localized in time, and it's sort of localized in frequency. You have this oscillation with period to the -n. Okay, so you can think about it as a square wave localized to this interval. Okay. Okay, I assume that many of you probably have seen them, but even if you haven't, it's quite easy to see that they are orthogonal, and this will actually be on your homework. It's pretty easy to see. If I take a smaller Haar function, then it will look like this, and when you integrate, when you take the product and integrate, you will obviously get 0. It's very easy to check. Okay, it's a little bit harder to see, and that's also your homework problem, but still very easy, that this is actually an orthogonal basis. With one addition, you need to add the constant function. So if you take L2 on 0, 1 and you add the constant function, you will get an orthogonal basis. If this formula looks a little bit weird to you, it's for a reason. It's because these functions, as I defined them, they're not normalized in L2. They're normalized in L1. Okay, they're in L infinity, I'm sorry. They're normalized in L infinity because the maximum of the modulus is 1. Okay, but the L2 norm, actually very easy to see. You square this function, it will be 1 on this interval, so you just get the length of the interval for the L2 norm squared. Okay, so it's somehow convenient in this theory to normalize in L infinity. We will see why, but we pay a price of having to have a slightly different form of this orthogonal expansion. So it's an orthogonal, but not an orthonormal basis in this form. Okay. When I put a star here, all I mean is that we've added a constant. Okay. All right, and then we can go to higher dimensions. Okay, and if we take dyadic boxes or dyadic rectangles now, so we take boxes so that all of its sides are dyadic, then we can just define the Haar function associated to this box or this rectangle as the tensor product. So basically a coordinate-wise product of Haar functions. So in 2 dimensions, it's going to look like this, like in this picture. Okay. And then again, tensor products of orthogonal bases are again orthogonal bases. So this system, when you added a constant in each direction, is again an orthogonal basis. We will actually not use the fact that it's a basis. We will just need the fact that it's an orthogonal system. Are there any questions so far? Is everything clear for now? Okay, now we will try to actually connect it to discrepancy in some way. Okay. And the main idea of Roth was not just introducing these functions, but also realizing how to use them and which part of the expansion to use. So the main idea was that if you take the expansion of the discrepancy function, dn, then the main part of this expansion is concentrated on the rectangles that are roughly of the size 1 over n, 1 over the number of points. Okay. So here I'm using this symbol very loosely. It just means that this is the main part, the part that carries the most information. Why is that so? What is the reasoning for this? Well, you can give some heuristic explanation. Basically, if the rectangles are too big, they usually capture too many points and there's too much cancellation and they don't give you too much information. For example, if you take the whole square, the whole cube, the discrepancy of the whole cube is 0, right? You have n points, so you subtract minus n times the volume, which is 1, and it's 0. Okay. If the rectangles are too small, too thin, or too small in size, they will probably either not capture any points or accidentally capture a point and give large discrepancies. So basically, they don't carry any meaningful information if they're too small compared to the number of points. However, if you look at these intermediate scales, if the size of the rectangle is roughly 1/n, then on the average you have roughly 1 point per rectangle, and somehow these individual discrepancies will add up. Main information is in these intermediate scales. So that was the main idea, but now we need to make it precise. Notice one thing that we can see right away. This will sort of explain where the logarithm comes from, because in this case, if the size of this rectangle is 2 to the negative n, and it's roughly 1 over the number of points, then little n has to be the logarithm of capital N. So we already sort of see where the logarithm will appear. Okay. Well, now let's start making this idea precise. All right. So when you talk about dyadic rectangles, unfortunately, the combinatorics becomes very complicated. In one dimension, you just have a system of dyadic intervals. They're all intervals. The geometry is the same. In higher dimensions, geometry becomes more elaborate. Even in 2 dimensions, it's already more complicated, and the higher the dimension is, the worse it gets. So we need to introduce some bookkeeping. So basically, we'll try to somehow keep track of different shapes of dyadic rectangles that you can get. So I'll introduce this set of integer vectors with non-negative coordinates, which add up so that the coordinates add up to 1. Okay, so basically what this is saying, this is just a little L1 norm. So the sum of the coordinates, these numbers are non-negative. The sum of the coordinates adds up to n. Okay. What this will do is this will keep track of different shapes. Basically, we would want the j side to be 2 to the negative rj. Okay, and then it's easy to see that then if that holds, then the size of the rectangle is 2 to the negative n. Okay. And if you fix the shape, so these vectors R that live in this set, they will correspond to different shapes. If you fix the shape, all of the dyadic rectangles are disjoint. So I have some pictures here which explain how this works. So this is in the simplest possible case, d is equal to 2, we're on the square, n is equal to 2, right? So you're looking at dyadic rectangles of area 1/4. There are only 3 possible shapes. Right? So there are 3 vectors that we can have with this property. If n is equal to 2 and d is equal to 2, we have 0, 2, 1, 1, and 2, 0. Okay. And these are the shapes that you get for those cases. Is this clear? I hope this is clear. Okay. All right. Okay. Now, in 2 dimensions, everything's easy. We can see that we have three possible shapes here. And well, if you increase n, you can see that you'll have n plus 1 different shapes. It's one of the reasons that 2 dimensions is much easier than other dimensions. If you get to higher dimensions, things become more complicated because you have a certain combinatorial explosion. If you count the number of such vectors, in other words, you count the number of different shapes of dyadic rectangles, that number becomes quite large. Actually, this is also a very simple homework problem. Okay, so this homework problem asks you to compute the number of such vectors. So this is the answer. So you just need to explain it. And then you can check easily that it's if d is fixed, if n goes to infinity, if n becomes large, this is roughly of the order m to the power d minus 1. Now, d minus 1 is pretty easy to explain in this case, heuristically, in the following way. If you don't have any restriction on the size of the rectangles, you can choose every side more or less freely. You can have n choices for every side. Right? But now you have a restriction on the size. That means you can choose each side in roughly n different ways, but then your last side will be fixed. Basically, you had d degrees of freedom, you're in d dimensions, but now this condition killed 1 degree of freedom. So the number of degrees of freedom is d minus 1. Okay. So that somewhat explains why d minus 1 comes in very naturally in these problems. Okay, and we will see in a moment how to finish this proof. Okay. All right. So now for every shape, we'll take rectangles of that shape, and we'll take Haar functions of that shape for rectangles of that shape, and we will multiply them by some coefficients, which will be just plus or minus 1. So this will be so-called generalized Rademacher functions, or just R functions, which basically look at the pictures. When all of the coefficients are 1, you got this perfect alteration of signs, right? So you get this all of these Haar functions, and signs perfectly alternate. So these are essentially Rademacher functions. If you've ever seen them, these are multidimensional Rademacher functions. But in this definition, we're allowed to flip some of the functions. We're allowed to put negative signs. So here the yellow rectangles are flipped. Okay. So these will be our basic building blocks. So these so-called R functions. And this explains the reason why we normalized these guys in L infinity, because now if you look at any of these functions, if you square them, they're just identically equal to 1. So their L2 norm is equal to 1. So they are convenient building blocks. And these functions are orthogonal because Haar functions of different shapes are orthogonal. Okay, so this is an orthonormal system. Okay. If you fix the signs, you get some orthonormal system. Okay, still we haven't gotten to discrepancy. It comes now. So remember, this is the discrepancy function. I wrote it in a slightly different way. So here, x, I put x in the argument. Basically, remember, we count the points that live in this rectangle with the coordinate x. So the point P is counted if it's here, or you can say the opposite. If x lives in this rectangle between P and 1, if x is here, then we can count it. Okay, so basically this is what we're counting. Okay. And now the discrepancy function has two parts. I'll call this one linear and this one counting. Okay. So one thing that you can easily check, let's start with dimension 1. Okay, if I take a function, indicator function of some interval q to 1 and integrate it against the Haar function, so that's just the integral from q to 1 of the Haar function. If that point q is not in the interval and this is 0, it's either to the right and then here you're just integrating against 0, or it's to the left and then here you're integrating against 1, which means, well, Haar functions have mean 0, so you get 0 in either case. Now you can easily extend it to higher dimensions. Now, if you have a point that is not in the rectangle, then the inner product or the integral of the product of these functions is going to be 0, because both functions break into products. So you can just suppose this function is a product of one-dimensional functions. This is by definition product of one-dimensional functions. So the integral breaks into a product of one-dimensional integrals, and at least one of these has to be 0. At least in one coordinate, the point will not be in the interval. Okay. So this tells us that if we found a rectangle that is empty, then if we take the inner product of the counting part of the discrepancy function with the Haar function of that rectangle, that's going to be 0. It's not going to contribute anything. Okay. So this is one of the important parts of this computation. Please stop me if there are any questions. Okay. Well, let's now deal with the so-called linear part or the volume part. Okay, so for the volume part, you can easily compute it again, because this has product structure, this has product structure, this just breaks into a product of one-dimensional integrals. Okay, and that is very, very easy to compute. I will actually skip this computation. You'll probably do it in the problem session. It's a super simple computation. Okay, so basically that tells us that if a rectangle does not contain any point of from our set of endpoints, then this part does not contribute anything to the inner product, and only this part matters, and when we've computed it. Okay, let's skip the next slide. Okay, and now here comes one of the main lemma, and the main lemma says the following: assume n, the number of points is in this range. Basically, assume we choose little n, we choose the scale so that this inequality holds. So, well, we just choose up two appropriate powers of 2. Okay. Then we can choose the signs, and we can construct this generalized Rademacher function so that the inner product will be bounded below by some constant. Basically, the projection of the discrepancy function on this generalized Rademacher will be large. Okay. Let me explain a couple things before I go to the proof. What does this mean? First of all, notice that this inequality means that little n is roughly of the order log n, log of capital N. This is what we already seen when we discussed the main idea. Also, you have to be a little bit careful here when you choose this. Notice that this means if this is your scale, n, little n is the scale, you have, for every shape, you have 2 to the n rectangles, right? Each one has size to the negative n, so you have 2 to the n of them, but n is less than 2 to the n minus 1. That means that for every shape, I wrote it in very small letters, at least half of the boxes will be empty. Okay? And we already know that for empty boxes, we can compute things. Okay? So basically, then the construction is very simple. Remember from the previous slide that for empty boxes, we got this relation. We got a negative sign, which is a little nested, but that's okay. We'll put a negative sign here for all empty rectangles. And for non-empty, we'll just choose the sign which makes the inner product bigger. So you have two different signs, plus or minus. Choose the one that makes things bigger. Okay, that will be exactly this. So this part will, when you take the inner product with dn, this part will have some positive contribution. We're interested in the lower bound, so we can just drop this part. So we'll only deal with the empty rectangles with this part. And for empty rectangles, we can just use the computation from the previous slide. And if you compute anything, you'll see number of empty boxes. Okay, you get the lower bound for n. Okay, and then you get the bound here. Okay. Okay, so the number of empty boxes is at least 2n minus 1 because of this, because at least half of the boxes are empty. Okay, so this is the idea. So basically, you look at the empty boxes. For empty boxes, you can compute the contribution of those Haar functions, and then you just need to guarantee that there are quite a few empty boxes. Okay? So it's an interesting interplay between analysis and combinatorics. And now it's more or less clear what happens next. We know that for different shapes, for different R's, all of these functions are orthogonal. So we found quite a lot of orthogonal functions so that the projection of the discrepancy function onto them is large. Okay, and we shall use this. So just like you do in geometry, linear algebra, you just use the for example, you can just use Bessel's inequality. There are two ways to extend this proof. You can do this by duality. Okay, so you can construct a test function, and by the way, this test function will be quite important. We will see it in the future in just a few slides. So basically, you take all of these functions that you've chosen in the previous slide. Okay, sum over all different shapes. Okay, so this has this form where all the coefficients are plus minus ones. Okay, and now we can compute everything quite easily. So first of all, what's the L2 norm of this test function, capital F? Well, all of these things have norm 1, and all of them are orthogonal. So basically, you just need to compute the number of shapes. And the number of shapes to the power 1/2. So it's little n to the d minus 1 over 2. Remember, this was n to the d minus 1, roughly. Okay, then from the previous lemma, again, we can compute the inner product, the projection of dn onto f. So we have each term here will contribute some constant, and we just need to count how many terms we have, and that's n to the power d minus 1. Okay, and then you just use Cauchy-Schwarz. This is Cauchy-Schwarz. This is of the order n to the d minus, at least n to the d minus 1. This is of the order n to the d minus 1 over 2. So you get this, and remember, little n is log of capital N. And that proves Roth's theorem. Okay, any questions about this proof? Okay, if not, just remember this function, because we will use it later. This function, you can think about this function as some sort of a model for the discrepancy function, because, okay, you're trying to prove a lower bound, you're doing it using an inner product or projection here. Well, if you wanted to maximize this, you would take a multiple of the discrepancy function itself. Well, but we see that if we take this function, we already get a lower bound, which turns out to be correct. Okay, so in this sense, this function is some sort of a model of the discrepancy function, which we'll use later. Okay, you can also do the proof without using duality. I will not go into details. It's of the same type, so you can just use Bessel's inequality. All of these Haar functions are orthogonal, so you use Bessel's inequality, and then you just restrict your attention to empty rectangles, and it's the same computation. I will not go into details. What I want to say, though, is, okay, we've proved the bound for the L2 norm. And I mentioned before, what would you do for the LP norm? Unfortunately, it doesn't extend automatically. So let's go to the duality proof, for example. If you want to extend this to the LP norm, if you want to put P here, you would need the LQ norm, the dual norm of F. So you would need to understand how to compute the LQ norm of F. Unfortunately, you cannot use orthogonality anymore, but there is a theory that actually lets you do that, and it's the so-called Littlewood-Paley theory, which tells you that the norm of this function in other LP spaces is also of the same order. Actually, if this were actually Rademacher functions, not generalized Rademacher functions, you could do it using Hinchin's inequality. Okay, but these are not Rademacher functions per se, so you cannot really do that. Okay. All right. So now let's go to the original question. Now we've proved Roth's theorem for the L2 norm, but the original question was what happens to the extreme discrepancy? How big is that? And the conjecture, and right now I'm being intentionally vague, the conjecture is that the L infinity norm, the extremal discrepancy, is much larger than the L2 discrepancy in order of magnitude. So it's of some order larger than log n to the power d minus 1 over 2. Heuristically, this could be explained as follows. If the set is distributed pretty well, then the discrepancy function most of the time should be pretty small. Okay? But sometimes it will have peaks, so it will be this very peaky function that's small most of the time, but then very large in some places. And in that case, if a function is very peaky, then the average norm is usually much smaller than the extremum norm, than the supremum norm. Okay. And in 2 dimensions, this is indeed known. So there is a lower bound of log n, which we will prove next. Okay, and it's known that it's sharp. Remember, in dimension 2, Roth's bound would have been 1/2. And here you have power 1 on the log. Okay, so this is strictly better than the L2 norm. And also turns out that it's sharp. It was actually known for a long time that it was sharp. It was only proved in the 70s that the lower bound holds. But constructions of sets with discrepancy of the order log n were known for a very long time. Some come, so there are basically two types of examples, Diophantine and digital, and I'll show you a couple pictures. So this is the digital example, the so-called van der Korput set, and you have some problems about the van der Korput set in the homework. Okay, it's constructed in the following way. You take points, you write them in binary form, okay? And you take the x coordinate with some binary number of lengths n, okay? The digits are zeros or ones. And for the y coordinate, you just flip the digits. And again, intuitively, the effect that it has that usually when you change the x coordinate a little bit, the y, so you change it somewhere here, the y coordinate changes a lot, so it changes here. So roughly speaking, this set is very, very well smeared over the interval, over the unit cube, unit square. Okay. Another example is the so-called irrational lattice. So that's built on the famous Kronecker sequence. So if you take an irrational number, let's stick with quadratic and irrationality. In the last lecture, I might tell you more. And take the fractional part of n alpha, and then just essentially draw a graph of that sequence. This is a lattice, and as long as alpha is a quadratic irrationality, for example, you get discrepancy of the order log n. Okay, actually, random points don't work as well. For random points, discrepancy will be much larger, or the square root of n. You can actually see from the picture, and it's not hard to prove that you're likely to get large gaps or some clusters if you use IID random points. Okay, all right. So what do we know about the L infinity discrepancy in higher dimensions? Unfortunately, things are very open. So construction that I just showed you is particularly the van der Korput construction. This could be extended to higher dimensions, and there are some other constructions in higher dimensions to obtain upper sets with discrepancy of the order log n to the power d minus 1. And many books, and I think even a Wikipedia page, say we'll call such sets low discrepancy sets, okay, because we don't know anything better. However, we still don't have appropriate lower bounds, and we don't even know what the correct conjecture is. So there are two different conjectures. So remember, we know the conjecture is that it's bigger than d minus, the power is bigger than d minus 1 over 2. Well, our first conjecture is log n to the power d minus 1. And that corresponds to the best known examples. Just because we don't know how to construct anything better, maybe this is the correct order of magnitude. There is a different conjecture, log to the power d over 2. And notice that when d equals 2, these are equal. So you get power 1, which we already know. Okay. But unfortunately, very little is known. So when I started working this theory with Michael Asen and Ren Vagarshakan, we proved that in all dimensions, starting from 3, you can indeed do a little bit better than d minus 1 over 2. But this number eta depends on the dimension. It goes to 0 as the dimension goes to infinity in our proof. So we cannot really, we don't even know that you get to d over 2, much less to d minus 1. There are certain disagreements between the experts as to which conjecture is correct, but I don't know. I hope that we'll find out in my lifetime. Okay, so now I will tell you a little bit about the proof of the L infinity bound. And this is actually not the original proof by Schmidt because it was pretty involved and pretty technical. This is the proof, the one that I will present goes back to Halas. It's much later in the 80s. And it uses a very interesting object. So here's what we're going to do. Instead of studying the discrepancy function itself, we will look at such sums of Haar functions, the sum of Haar functions over rectangles of fixed sides. Okay, remember a few slides ago I told you this is the test function, so I will use this. This is a model for discrepancy function, so I will use this to avoid technicalities. Okay, and there is a conjecture with a slightly weird name called the small ball conjecture. And the name comes from probability, because I will not get into those details now. But it basically, it is a conjecture about the L infinity norm of such sums. It might be hard to read right now. It's a little bit strange. It's the important thing here is this d minus 2 in the exponent. It's the conjecture is known in d equal to 2, and I will show you the proof in just a second. And it's, if it's true, it would be sharp. It's known, and there are quite a few things that are known. But in dimensions 2 and 3 and above, the only thing we know is that you can do a little bit better than d minus 1 over 2 here. Okay. It should be minus. Sorry, if you write it this way. Yeah. Okay. The conjecture, if you replace this d minus 2 over by d minus 1, it becomes very simple. It's almost the same computation that I showed you for discrepancy. Okay. You just use the Cauchy-Schwarz inequality, and it's very easy for the same reason that the number of terms is of the order n to the d minus 1, and the number of different shapes is of this order. It's very natural to get this power d minus 1 over 2 here. Okay, so it's exactly the same computation that I've shown you for the discrepancy function. So d minus 1 would be easy. So you can also view, there is a simpler version of the conjecture, which is still also very open. If you put all the coefficients plus or minus 1, so you have the sum of these generalized Rademacher functions, then it's even easier to see the L2 bound. Actually, if you take the original conjecture and put plus minus 1s here and simplify things, check this. This is what you will get. Okay, now maybe you're already recognizing this d over 2. Okay, and it's very easy to see. You use orthogonality and you get d minus 1 over 2 very easily, but you want d over 2 in the conjecture. So this is the similarity between the two conjectures. If you say, let's say just the sign small ball conjecture for simplicity. So for the signs, if all the coefficients are plus minus 1, you're saying that this should be at least of the order n to the d over 2. Discrepancy, our conjecture 2 was almost exactly the same. This is log n, the number of points, to the power d over 2. So in both cases, you gain a square root over the L2 estimates. So in this conjecture, since we know that this conjecture is sharp, actually motivated the second conjecture for the discrepancy. Okay. Or in particular, these methods will only prove this bound. If we want to prove larger bounds, there should be completely different methods. So I will show you the proof of this inequality in the next 5 minutes. So do you have about 10 minutes? I started a little late. Is that okay?
Yeah, you certainly have time.
All right. Yeah, thank you. Thanks. Okay. So yeah, before I show the proof, so a couple things. So here is just a comparison of results about discrepancy and about the small ball inequality, and you can see that they're essentially parallel. So here's another thing that's somewhat open. There is no theorem that says that one would imply the other. So I would assume that it's probably possible to say that if you prove an inequality for such sums, maybe with arbitrary coefficients, not just plus minus 1, then this should imply bounds for a discrepancy. But so far, these implications are more in the methods of proof. We cannot really prove a theorem, but if you use the method usually transfers. Okay, so that's why the small ball inequality, once again, can be viewed as a model, as a linear, simpler model for the discrepancy function, for the discrepancy estimates. Okay, and now I'll go to the proof, but before I go to the proof, I need a couple more properties of Haar functions. I'll start with two-dimensional Haar functions. Well, we have this property. If we take two rectangles which do not coincide, two dyadic rectangles which don't coincide but have the same size, and we take the product of two Haar functions, it doesn't just have mean zero by orthogonality, but we even know more. We know about its structure. It's you will get up to plus or minus, you will get another Haar function. It's sort of clear from the picture, and you have this problem in the homework. It's very easy to figure out. But what this tells you is that you have even more. You can now keep multiplying more and more Haar functions of the same size, and you will get orthogonality. So again, that's a problem in your homework when you have several Haar functions on rectangles of the same size, but which do not coincide. Okay, then if they all intersect, the product will give you a Haar function of the intersection up to plus or minus. So basically, I could extend this property to more functions with the same property. None of them coincide with each other, and all the sizes are the same. So this is very nice. This almost gives you some sort of independence, right? It's like the expectation of the product is equal to the product of expectations. Or they're non-correlated in a sense. Unfortunately, and this is one serious source of problems, this is not true in higher dimensions. In higher dimensions, you could have two boxes of the same size, okay, of the same volume, but they could coincide in one of the coordinates, as in this picture here. And that means when you multiply Haar functions in that coordinate, you will get an indicator function, right? So in that coordinate, you will lose orthogonality. So you take Haar function squared, that's just 1 on that interval. And then if you multiply more functions, you could end up losing all of the orthogonality altogether. That's a big source of problems, and that's why higher dimensions are so much harder than 2 dimensions. But now I'm ready to give you the proof of the of this small ball inequality in 2 dimensions. So remember, this is the function that we need to estimate with L infinity norm we want to estimate. We will use duality. If we want to use duality, we will use L1. So we want to construct an L1 function. Okay, and we construct it in the form of the so-called Riesz product. Okay, so here's what I do. I take these functions fk. So these correspond to different shapes. Okay? So you have this side is 2 to the negative k, this side is 2 to the minus n minus k. So these are these generalized Rademacher functions, and I choose the signs here, plus or minus 1, just as the signum, the sign of your coefficient. Okay. All right. So all of these functions are just plus minus 1 at every point. And now I take this product. Okay. Actually, it should be from 0, but not super important. Okay. All right, let's see, what do we know about this function? The reason we're doing it, imagine that these were Rademacher functions. Okay, if they were independent, then this would be, all of these factors would be independent. You take the product and integrate it. You can put the integral inside the expectations. You can put it inside, and then things work. Things are nice. It's easy to compute the integral, the expectation if these were really independent. In a sense, these guys still behave as if they were independent. So here's the computation. Here's the argument. First of all, since this only takes values plus minus 1, that means that this is always positive, non-negative. So the whole function c is non-negative. Okay. Second, and this requires a little bit of explanation. If you integrate c, you will get 1. Okay, why is that? Let's just take this and multiply everything out. Okay. You'll have the leading term 1. You integrate it, that's 1. Then you'll have linear terms which just contain one function. They are sums of Haar functions, so their integral is 0. And then you have products. You have higher order terms. You have these products, and they but by the product rule that we just discussed, they're again Haar functions, and their integral is again 0. Okay, no matter how many of these guys you multiply, since the volume is fixed, the products will be 0. So everything else integrates to 0. So only the leading term contributes 1. Okay, and well, these two properties then mean that the L1 norm of this function is 1, so it's a good test function for estimating the L infinity norm. So you just use the stupid case of Hilbert's inequality, right? This is smaller than the L infinity times the L1 norm. Okay, the L1 norm is 1. Okay, and now you compute this inner product. So you integrate this function against this function. Okay, but now the same thing happens. All of the products of Haar functions will give you 0. Okay, will give you integral 0 because they again will be themselves Haar functions. The only time you get something non-zero is when you hit linear terms here, when a Haar function from here hits the same Haar function in here. Okay, and in that case you will get alpha r times the signum of alpha r, which is the absolute value, and then you'll get the inner product of HR with itself, which is 2 to the negative n. And this is exactly the inequality that we wanted to prove. Okay, let me go back for a moment and show you the inequality. Yeah, that's so in the case when d equals 2, this is gone. Right? So that's exactly the inequality we're trying to prove. Okay. All right. So in the next couple of minutes, I promise I won't do any more actual math, but I would just want to give you some philosophy and some connections with these things. So Riesz product, it's a very interesting object which comes up in functional and harmonic analysis quite often. In particular, it came the first time, at least to the best of my knowledge, the first time it came up was in the work of Sidon. Actually, that must be wrong because otherwise, why would it be called Riesz product? I'll have to research the history. But there is a pretty famous theorem of Sidon which says the following: you have lacunary Fourier series. So think of an Adamar lacunary sequence, so where every next term is greater than some multiple of the previous term, some multiple greater than 1. Okay, so the ratio between, think about 2 to the n or 10 to the, sorry, 2 to the k, 10 to the k, like this, something that grows exponentially or super exponentially. Okay, so if you have a function with lacunary Fourier series, okay, you can put cosine here instead of the complex exponential, for example. Then the supremum of this function is bounded below by the sum of the coefficients. The opposite inequality is obvious. Okay, you just put absolute values inside, and all of these guys are bounded by 1. But the lower bound, well, with some constant, with some absolute constant, is non-trivial. In particular, this immediately implies that if a function, if a bounded function has lacunary Fourier series, then its Fourier series converges absolutely and uniformly by the Weierstrass M test. Okay. And it's a very interesting property. Lacunary Fourier series in general is a very interesting object. It provides one of the first examples of nowhere differentiable functions. And many other interesting properties. But a way to prove Sidon's theorem, and I think it's the original way Sidon proved it, is using a Riesz product, which looks like this. And actually, it's a very similar Riesz product. Well, here I use Haar functions, generalized Rademacher functions. So you use oscillations like this in each direction, only maybe if they're flipped on some parts. And here I use the cosine, so you use oscillations like this. Okay. It's not surprising that these theorems are so similar because, well, here you have lacunary Fourier series, and here you have an object. Well, this, remember, we're in 2 dimensions, and then we impose this condition, which effectively leaves you with 1 free parameter. So this, in some sense, a 1 parametric family. Okay, it's a 1 parametric family whose frequencies behave in a lacunary way. Remember, so we only look at intervals of length 2 to the negative n. So that's lacunary. So the frequency is 2 to the n. So it's a lacunary sequence. Actually, if you want to prove this when lambda is very, very large, think about lambda equal to 10, or 100 or whatever. Some number large enough, doesn't have to be very large. Then it's not so hard to prove, because you take the first oscillation, okay, and then choose the parts where it's large. Okay, choose these intervals. Okay, but then let's zoom in into one of those intervals. Okay, so here is one interval, and then I take the next oscillation, but the next oscillation has a much higher frequency, so it will oscillate here. Okay, and there will be intervals where the next oscillation is large within the previous interval. Okay, and then you can keep going like this, and essentially you're constructing a Cantor set, a Cantor type set of points where this function is big. Okay. So, but it only works for large lacunarity, but basically whenever you deal with something lacunary, the first thing you should check is what happens with large lacunarity, and then you actually need to work to see what happens when the lacunarity is smaller, because you can take lambda very close to 1, and then things will get much more complicated. The proof of this theorem, parts of it will be discussed in the problem session, and some parts are in the homework. And it's a proof using a Riesz product like this, with an argument very similar to the one that I just described. Okay, and yeah, so these are the similarities. There is a second theorem of Sidon, which says that the L1 norm is bounded below by some constant times the L2 norm for the lacunary Fourier series. Again, the opposite inequality is true for all functions. Okay, but basically this tells you that for lacunary Fourier series, all LP norms are comparable to each other. And this is also proved using a Riesz product of a very slightly different structure. So you need to go into complex numbers. And there is a similar bound for the L1 norm of the discrepancy due to Halas, which is also proved using a Riesz product, okay, of this type. So it's a very funny connection, which is not completely understood, the connection between lacunary series and discrepancy function. It's both of these bounds using Riesz products were proved by Halas in the same paper. I suspect he probably read Sidon's papers right before that, or the exposition in some book. Okay, and yeah, so I've abused your attention. I just want to briefly, just 1 minute, I'll remind you about the Van der Corput set, because we also have some problems and discussions about the Van der Corput set. So remember, it's written, the constructor is written in the binary form, binary digits, 0s or 1s, and then since you have n digits, you have 2 to the n points. Okay, and it has optimal discrepancy, which you will prove in homework. It has many interesting properties. So here I'll just show you some pictures. In particular, again, you'll need to prove it in the homework. If you take any dyadic box of size 2 to the negative n, it will contain exactly 1 point of this set. Okay, which will mean that dyadic boxes have discrepancy 0. Okay, and then you can go from that to prove that general boxes have discrepancy of the order log n. So these are pictures of the Van der Corput set. You see that it is indeed very well distributed. Although as number of points grows, you can see that there are some defects. For example, here, sometimes, and if you think about it, you will realize which points that those are, but sometimes there are couples of points which get very close to each other. You see that more and more as you increase the number. But generally, you see that they cover the unit square pretty well. Okay. Also, there are lots of interesting properties. For example, they're actually projections of the unit cube, which is also quite easy to see if you think about it for just a couple of minutes. I will stop right again. I'm sorry for being a little late, and sorry for going a little over time. Thank you very much for your attention. I'm ready to take questions. I think we can stop recording, and then I can take questions. Are there any questions?